Hi, my name's Percy. In the device you're using to watch this video, there are probably more components than there are people in your country. Those components work together in a complex dance to do billions of calculations every single second. Over the last 11 months, I've worked with two friends to try and distill that complex dance. We've built a central processing unit. In this video, we're going to tell the story of how we got there. In October 2021, the Mark Everson Foundation visited my school and gave an assembly. As it turned out, they were offering up to £500 to students who wanted to do a complex project. This is a seriously enticing amount of money, and I took the opportunity to do something I wanted to do for a long time, to build a CPU. And to say this was going to be a challenge would be an understatement, and so I formed a team with two other students to suffer with me.
Hi, I'm Marcel. I joined because I was told we were going to build a rocket.
Hi, I'm Neil. Before beginning to build a CPU, it is first important to understand what a CPU even is and how they work. Often considered the brain of a computer, the CPU is responsible for running all of the programs and apps you use on your computer, phone, or other digital device. These programs contain thousands of instructions coded in binary, that's ones and zeros, which the CPU can interpret as either the presence or absence of electricity. Add, sub, store, and load are examples of instructions which a typical CPU is able to carry out. The electricity represented by an instruction and its operand can be manipulated by logic gates to produce an output. There are four main types of logic gate, each of which operates slightly differently, as shown on the screen.
We decided to build the CPU, which we call the Mark Lambda, on breadboards because of shared experience in using them and simplicity. No solder was required. This all proved advantageous for budgeting. The Mark Lambda was to be an 8-bit CPU of integrated circuits containing logic gates. To get approved for funding, the Foundation required an application containing a general proposal, risk assessment, table of costs, and various other admin type things. During this time, we had already started rough designs of our CPU in diagram maker diagrams.net, formerly known as draw.io. Over the application process, some revisions to the proposal were made, mainly having to change to a 4-bit CPU. After approval of our application, we were cleared for funding from the Foundation and started working on a low-level schematic.
This schematic basically takes our initial high-level schematic and goes into much more detail. To design this, we used a piece of software called Digital, which can simulate logic circuits. For example, in this circuit, the output won't light up if either input is off, but will light up if both inputs are on.
Also, Digital allows us to create tests that make sure our circuits work as intended. For example, this test here makes sure that this circuit behaves as we expect it to. If we swap the logic gate for a different one, the test will now fail and will appear in red. This proved to be quite useful in our more complex circuits where we couldn't know for sure if a small change had broken a larger part of our design.
The low-level schematic outlines how each component in our CPU works, and how exactly they interact with each other. So for example, the ALU in the high-level schematic looks like this, while in the low-level schematic it looks like this. As you can see, it's a lot more complicated, but also a lot more representative of what the CPU actually looks like in real life. And even better, with this schematic we could actually simulate the CPU to check if everything worked. Basically, for every instruction we created a test, which let us check if the CPU was still working after making a change. And of course, everything that could go wrong went wrong.
In fixing all that, the corrections and adjustments we had to make drastically changed the CPU. Some components didn't even function as we had expected, which caused hours of confusion as we tried to figure out what the hell was going on. Some of the components didn't even exist in digital, so we had to make our own versions. And even after this ordeal was over, we still had absolutely no clue how to lay out all the components on our breadboards.
You see, each chip has about 16 pins to which we can connect wires. And there are 202 chips in the CPU, and each pin needs to be linked to another pin, meaning there are about 1,600 wires. Of course, having this many wires in such a small space can get messy to say the least. We needed to have a good idea of where these wires would go and how we could place different parts of the CPU together so that we wouldn't end up with a jungle of wires. We did anyway, but that's beside the point.
What this all meant was that we needed another schematic, an even more complicated schematic that would show us exactly where every single chip and every single wire should go. This took a long time, a really long time. In fact, we recorded it, and there's over 140 hours of footage. By the time we were done, digital was running at 20 frames per second, and it took several seconds just to undo something. After this, Wait, no, we're getting ahead of ourselves. Commence the error montage!
This schematic is the bane of my existence. Imagine all the issues from the first design times 1,000, plus several new errors, plus having to route wires all over the place, and you start to get the picture. It was absolutely soul-draining, but after a huge amount of work, the new schematic was finally complete. Now that all the hard stuff was supposedly out of the way, all we had to do now was translate the schematic onto the breadboards. Breadboards basically allow us to connect electronic components together. All the pins going into a row will be connected. For example, with this setup, the LED will light up, but with this setup, it won't.
The whole process of building the CPU happened individually for each breadboard, thereby making the testing phase much easier. With this approach, we could make sure each individual breadboard worked, rather than trying to test everything at once. Firstly, we'd place the chips for the breadboard down, and then cut wires to length and strip them to expose their metal ends. Now, we just need to do this for about 40 breadboards. Easy, right?
Almost 380 cumulative hours of building later, we had built the majority of the CPU. After all the breadboards had been connected, it was time to start testing the CPU. With the first few tests, the instructions were manually sent to the CPU by physically moving wires on the breadboards. This is how all the initial testing was done. Inevitably, absolutely nothing worked at first. It took over a week of testing and debugging to get the first instruction running properly. Once that was done, we connected the CPU to a miniature computer known as a Raspberry Pi. This meant we could now write software to test the CPU rather than doing the tests manually.
There are lots of advantages to using software as opposed to doing the test manually. It's a lot faster and more accurate. And since we can run the tests so much faster, we can run a huge number of tests. And the more tests we run, the more certain we can be that the CPU is working correctly. All in all, the full set of tests contains about 400,000 tests and takes over 15 minutes to run. Also, we had the idea to add debugging functionality to the software, so whenever a test failed, we could repeat it and go through each step bit by bit, pun intended. This really sped up testing, and the time that it took to fix each problem went from 4 to 5 hours to just 1 to 2 hours.
With our CPU having the ability to run custom written programs, we decided to create an assembly language and assembler to make the creation of such programs easier. Programming in raw binary is not something we were keen to contend with. Known as the Lambda assembler, our assembler not only allows for the use of our CPU's native instruction set, but also extends this by adding additional instructions such as call and do until, which can be used to simplify the process of writing complex programs.
At the time of making this video, we have 13 out of 19 instructions working, and we're positive that we should have the next 6 instructions working within a month. We've recently run some showcase programs to demonstrate what the CPU is capable of at our school's open evening, and once the project is fully complete, we intend to put it on display in our school, with regular maintenance and improvements.
Well, that's just about it. In the coming months, we'll hopefully be working on some longer form videos which will dive into how the CPU actually works in much more depth. Additionally, we're working on a website for the project, which we'll link down below in the description when it's complete. Finally, I'd like to extend my wholehearted thanks on behalf of our team to the Mark Everson Foundation. We simply couldn't have done this project without them. If you wish to donate and allow them to continue supporting projects like ours, there will be a link to our Just Giving page down below, as well as links to the Foundation's website. Thanks for staying this long, and have a good one.